guys, so in this video I'm going to talk about derivatives of inverse functions and logarithms. And logarithms are always related to inverses. So there's kind of this strange property, odd property that have to do with derivatives and inverses and functions. So I want to build up to it. So what we're going to do is we're going to find the inverse of these two functions. So if you want to pause the video here just to see if you remember this would be a good spot to do that, and then hit play when you're ready. So for the first one, so the way that you find an inverse, so you flip your x and your y coordinates like this, and then you solve for y. So if I solve for y, so normally I would get y equals plus or minus the square root of x, but since I've actually restricted the domain up here, I don't need the plus or minus, so I can just say that y equals the square root of x. So what this actually means then is, so we always then renotate this as y inverse equals the square root of x. Okay, so there's one inverse. And now for the other one, so once again, so I flip my x and my y, so I have x equals y cubed plus 2, and then I solve for y, so I subtract the 2, so I have y cubed equals x minus 2, and then y equals the cube root of x minus 2, so now I just put the inverse notation on this like this. Okay, so here's my inverse, so I got my two inverses. Now, next part of this, I want you to select a random point for each function. So any point that you want, I'm going to select my own. So maybe pause the video, just choose something at random. Ideally where you have two different numbers as your x and y coordinate. Okay, so for me, I chose 3 and 9 for my y equals x squared, so 3 squared is 9. And then for my other one, so I chose -2 and -6. So if I plug -2 into this and I do all the calculation, I'll get -6. And so here's the thing then that I want to just notice or point out. So what happens to these points with the inverse? So what can I say about these points how do they relate to the inverse? So this is just a way to remind you actually that what makes an inverse is that it's just the x and y coordinates from the original function. It's just those points flipped like this. So I wanted to just point that out to you. Now, remember the points that you chose, or if you're using my points, then we just keep these in the back of your mind, okay? Personally, I think this works a little bit better if you've chosen like another set of points so that you can kind of drive this point home in a few different ways. Okay, so moving on. I now want to take the derivative of each function and its inverse. So the derivative of x squared, that one's nice and easy, right? So that's just 2x. And then taking the derivative of my inverse, so the square root of x. So this is going to come out to 1/2 x to the -1/2, and we'll reformat that in a second. So now let's move on to taking the derivative of these two functions. So if I take the derivative of my y function here, so that's just going to be 3x squared, that's my y prime. And then my inverse, the derivative of my inverse, so I got to use the chain rule here. This comes out to 1/3 x minus 2, all of that to the -2nd. Okay, so now what I want to do is I want to ask this question of how are the points that we found, how are they related with their derivatives? So there's this kind of odd relationship with functions, their inverses, and their derivatives. So here's everything that we have found so far, right? So here's my function, here's the inverse, here are the derivatives of those inverses. So here's what I'm going to do. Remember that point that I chose at the beginning. I used the point 3, 9. I am going to calculate, so this is y inverse prime. I'm going to plug 9 into this function. So I'm going to plug 9 into this function here. So if I do that, so I've got 1/2 times the square root of 9, so that'll just come out to 1/2 times 3, so it's just going to be 1/6. Okay, now what I want to do is I want to take y prime of 3, so I'm going to plug 3 into this. So remember, 3 and 9, this was a point, right? These had a relationship, 3 and 9. It's not like I'm just choosing anything random. So I'm choosing something, these two numbers that already had a relationship. So if I plug 3 into y prime, I will get 2 times 3, which is 6. And so here's the strange relationship. These are like reciprocals of one another. Or this is one over the other one. Okay, So I want to do that one more time. And if you were playing this along with your points, then you should have gotten the same thing as well. So we can see this pattern kind of establishing itself. Okay, so now working with the other functions. So here was everything that we found, right? So here was my y, my inverse, and then the derivative of each. So same thing. In this case, I had the points -2, -6. So I'm going to take y inverse prime of -6. So I'm going to plug -6 into this guy here. And so if I go through and I work this out, so I've plugged in my -6. So I'm going to have, this is really going to come out to 3 times -8 to the 2/3. So remember, how do you evaluate this? First, you take the cube root of -8, which is -2, and then -2 squared is +4. So this will come out to 1/12 when all is said and done. Okay, so remember, -2, -6, that was the point that we chose. So now what I'm going to do is I'm going to plug -2 into my y prime here. So if I work this out, so I plug in -2 like this, what do I end up getting? I get 12, and hey, look, you've got that relationship again. So this is like a very strange type of relationship to point out. It takes a little bit of work to get there, but it's actually a really handy property, and I'm going to show you why in a second. So this little relationship that we see, this is actually the derivative rule for inverses. So to set this up, so you've got to have a function f of x, and it's got to be differentiable, and it's got to have an inverse. And then you're going to have some point AB from your function. So then BA is going to be on your inverse. And you have to have that both of your functions are differentiable. So there's a lot of things you need for this to work. But when all that happens, here's that relationship. So this is actually kind of what we were looking at. So f inverse prime of B from our point will be the same as 1 over f prime of A. So, and actually, if I rewrite this, I can see this relationship between how the derivatives and the inverse all kind of play off of one another. So this is a formal relationship. So how does this help us? I want to use this rule to help us find the derivative for the natural log of x. So you can find the derivative of the natural log of x in more than one way, but I just want to use this rule since we just learned it and it's cool. Okay, so here was the property, right? This was the property I just showed you. And so the one thing I just want to remember here is, so e to the x and the natural log of x, those are inverses of one another. So just keep that in mind. So what I want to do here is I know the derivative of e to the x, but I don't know the derivative of the natural log of x. So what I'm going to do is I can take the derivative of e to the x, which is just e to the x, and I'm going to use that as my f prime because I know that derivative. So I've got e to this f inverse of x. So what is the inverse of e to the x? Well, we said it was the natural log of x. So let me replace that now with the natural log of x. And this here, this is a property actually. So this is one of the properties just of logarithms. So this equals just x. So what this means is the derivative of the natural log of x is equal to 1 over x. So there's that point all summarized for you. So this is a new derivative that we're going to add to our bag of derivatives that we know. So that covers it for this video. So thanks for watching, guys. I have some other videos where I actually show you how to take derivatives of this. This was just to kind of establish the rule and why this derivative equals what it is. So I'll see you guys next time.